Now let's look at the other possibility, which was having the magnet move towards the coil, right? You saw in the demo that that also worked as good, just as good as moving the coil, right? That's the magnetic field, but now we're moving the magnet. The observation that there is a current flowing here cannot be explained by motional EMF because the charges of the coil inside the coil are not moving. I said I'm going to leave the coil stationary. It is the magnet that is moving. So there has to be something else that can explain that, some other physical principle going on. So to understand that, we're going to have to start with the idea of magnetic flux. So imagine a river that has some current, and you decide that you're going to use some of that water of the river for, say, irrigation. So you put a pipe here. You immerse a pipe there to try to intersect as much water as you can from the river, right? Now, how much water you're going to intersect? This is the current of the river, right? How much water you're intersecting and being able to make go down this pipe depends on three things. The first is the area of the pipe. A bigger pipe would intersect a bigger amount of water. So that's pretty clear. It also depends on how fast is the current in the river, right? A faster river moving will bring more water per second than a slower moving river, right? I'm not talking about using a pump here to suck the water out of the river and just putting a pipe there and seeing the water, how it flows out of that pipe maybe at some other location nearby. So the flow is also going to be proportional to the speed of the river, right? Or the current in the river. Let's call it the current in the river. And what's the third? The direction. It's not the same to put a pipe facing this way than to put a pipe facing this way, right? If the cross-section of the pipe is right across, or it's intersecting the current in the river, then you're good. But if the pipe is facing this way, then the water would have to kind of bend this way, 90 degrees, to get into the pipe, okay? So that's not as easy as just having the pipe facing the current. So the flow that you intersect with your pipe, to summarize, depends on the area, it depends on the current of the river, and it depends on the orientation of the pipe. Okay? For magnetic field, we're going to define, and a circuit, we're going to define a quantity that is very similar. We're not going to call it flow, we're going to call it flux. Just to make a little distinction there, that we're not talking about something that is physically flowing, like water, right? And the magnetic flux, we're going to define it this way. We give it the letter phi, and it's going to be B, the magnitude of the magnetic field, A, and the cosine of the angle between B and A. So this is what I mean. You would have magnetic field lines in some region of space. Say that that's the B lines. And then you have a coil, a circuit, a closed circuit that has some area. That's your area A. And that circuit is oriented, or that coil is oriented in a particular direction. So the way I'm going to define the vector A is going to be, it's a vector that has magnitude equal to the area of the coil, right? And the vector direction is going to be perpendicular to that area. So when the vector A is aligned with B, you will get maximum flow, right? If the vector area, say that you put your coil like this, with the area pointing this way, then the phi is equal to 0 for this arrangement, because the magnetic field lines are going like this, and they don't go through the coil. So you say that the flow, the flux, the magnetic flux through that coil is 0 in this case. Not so in this case. Okay? So magnetic flux it's an important concept, because in terms of that magnetic flux, we can write or we can put a bunch of observations about induced current in terms of the magnetic flux and how it is changing. So that's why we use it. Notice one thing about the magnetic flux, which is that if only part of your coil is intersecting magnetic field lines, right? This is your whole area, but not the whole area is intersecting the field lines, B. Suppose that the B magnetic field is only limited to be in this part of space. Your flux is not going to be B times A, right? It will be B times the area that is immersed in the magnetic field. Okay? So in principle, you should write phi as being the integral of B dot dA. If there is B here, then you get a B dA contribution. But if there's no B on the left-hand side, then that area does not contribute. All right? So it's only the part of the area that is in the magnetic field. Just be careful with that. So that means that if you have, for example, a magnetic field in this region of space, and you have a coil partially immersed there, as you pull this coil away, the flux through that coil is changing. Not because the area of the coil is changing, but because the area of the coil that is immersed in the magnetic field is changing as you pull it out. Okay? So that will be an example of a changing flux. So with this idea of magnetic flux, now we're ready to talk about Lenz's law. The induced current in a circuit, in a closed circuit, right, only occurs if the magnetic flux changes. Change is the key word here. And you have to look at the magnetic flux. It's not enough to look at the magnetic field. You have to look at the dot product between B and the area of the coil. So that's the first observation. There will be an induced current in a circuit if the magnetic flux going through it changes. The second part of Lenz's law tells you the direction in which you would expect this current to flow. So that's also very important. You need to know whether there is a current, and once you know if there is a current, you need to figure out in which direction is that current flowing. Okay? So Lenz's law tells you that the direction of the current is such, direction of the induced current, that's how I'm going to call it, is such that the induced magnetic field opposes the change in flux. So to be able to use Lenz's law, you have to have several things. There has to be a magnetic field somewhere in space, right? So what you have to have is this. You have to have a magnetic field. That was provided in our little demo by the magnet. You must have a conducting loop. And you must change the magnetic flux through the loop. If you do all those things, what's going to happen? Right. Lenz's law tells you, number one, there will be an induced current. If there is an induced current, there's going to be an induced magnetic field. You will get an additional magnetic field going in your problem, which is not the same as the magnetic field whose flux is changing. Those are two different magnetic fields. Okay? I will explain that with an example. So let's look at a particular example, just like in the demo. Let's say that you have a south pole and a north pole, and the magnet is moving with velocity v towards a loop that I'm going to diagrammatically represent here by having a loop cut in half. Okay? So there's going to be a current flowing here. I'm going to specify the direction of the current on the top and at the bottom of the loop. So first question you have to ask yourself is there a flux that is changing in the coil? This is the coil. So the flux, it's going to be the flux due to the magnetic field produced by the magnet. Right? That's the external magnetic field. So once you figure out that there is a flux, next ingredient is the flux changing? if you move the magnet closer to the coil, the flux is changing because the flux is B times A, right? Or the integral of B over times A. The area of the coil is not changing, but the B at the location of the coil is changing. Okay? We're not saying the B on the magnet. We're saying the B at the location in space where you have placed your coil. So that B is changing. If B changes, phi changes. If phi changes, you're going to use Lenz's law because there will be an induced current in that coil. Correct? Now the question is, how do you figure out the direction of that? So now we're moving on to the second part of Lenz's law that tells you in which direction you would expect that current. So that second part of Lenz's law says that the induced current in the coil is going to be in such a direction that the induced magnetic field would oppose the change in flux in the circuit. So this is what I propose that you do. Draw a little vector representing the flux. I know the flux is not a vector, it's B dot A, but you can assign a vector to that flux. Goes in the same direction as the magnetic field. Okay, with magnitude B times A. Now, what happens to that flux? If this is the flux at some initial time, what is the flux at a later time when the magnet got closer? That will be a bigger vector. This is your phi final, right? Calculate what's the difference in phi as a vector. In which direction delta phi points? If the final phi is bigger than the initial phi, delta phi, remember that it means final quantity minus initial quantity, right? The final vector is bigger than the initial vector. So therefore, when you subtract this big vector and you subtract the smaller one, you still get this pointing in that direction. The change in flux through that loop is pointing to the right. The flux is increasing. So now you got your delta phi pointing that way. Lenz's law says what? The induced magnetic field is going to be opposite to your change in flux. So that tells you what's the direction of the induced magnetic field, right? Opposite to that vector that I just drew there. So the induced magnetic field is going to have to point that way. How do I get the coil to produce a magnetic field inside the coil that points to the left? The current either flows one way or the other, right? On the top wire, it's going to have to flow which way? You use your right-hand rule in the Beer configuration, right? And you can put your fingers in the direction of B induced, which is pointing to the left. That tells you that at the bottom wire, your current is going to have to come out. And on the top wire, your current is going to have to go in. So that you produce an induced magnetic field that points this way, which opposes the direction of the change in flux in the circuit, in the loop. Let me remind you of the steps that we did here. There is an external magnetic field that has to be applied to this coil. The coil must be immersed in a region of space where there is a magnetic field. We had a B here because we had a magnet. Second element is that the flux through the coil, there has to be flux through the coil, first of all, right? If there is B, you're not guaranteed that you have a flux, right? Unless the coil has some perpendicular area to the B. So there is a flux, fine, that's good. But also the flux needs to be changing. And the flux is changing because the magnet is getting closer to the coil, which makes the magnetic field at the coil grow in intensity. Now that you figure out that the flux is changing, you can move on to the second part of Lenz's law that tells you the direction of the induced current. So for that, I suggest, you can do it whichever way you want, but I suggest that you draw those two vectors, the flux at some initial time and the flux at some final time. For this magnet moving in towards the coil, the final flux is bigger than the initial flux. So when you subtract those two vectors, final minus initial, you get a vector that points that way. This is your change in flux vector. If the change in flux vector points to the right, the induced magnetic field is going to have to point to the left. The final step is to translate direction of magnetic field into direction of the induced current. Right? The direction of the induced magnetic field inside the coil is to the left, so when you use your right-hand rule, that tells you that at the bottom wire, the current should be coming out.